events.
So this is IPv6 an update featuring IPv6 mostly, which is a relatively new technology or set of technologies, set appropriately. And let's get started. So I'm with Hexabuild. We were created and designed specifically to help organizations deploy IPv6. All of our architects have at least 10 years deploying IPv6 experience. You can see that we have 4 published authors to include myself. If you've heard the Packet Pushers podcast, we actually have a podcast channel called the IPv6 Buzz on Packet Pushers. There are 146 episodes there. Great place to go pick up some knowledge on specific technologies within IPv6 so you can peruse the catalog and find information from the past as well as the relevant updates that we're seeing. You'll notice that we participate in the IETF, the development of the IPv6 protocol itself. Lots of training all over the world and plenty of different locations and events. And we've been consulting numerous Fortune 100 as well as the vendors that you are familiar with. We have consulting engagements with Cisco, Microsoft, Arista, and Juniper. So we really do know the IPv6 landscape and anybody who has ever really participated in that landscape. Just a quick blurb about myself. 40 years in networking technologies. Got my start. It was a great place to start in the U.S. Army. 1983, I enlisted and got sent to a school to learn RF theory. After finishing a year of RF theory and multiplexers, I got sent to a unit that was chartered with installing broadband CATV for data, not for video, and baseband Ethernet. So literally 40 years ago with that great place, the U.S. Army. Over the years, I've continued to evolve and continued to focus on the internet protocol. So let's look at that worldwide adoption, because a lot of people aren't familiar. So if we look at the bottom, lower left, you see that we actually flipped the switch for IPv6 on the global internet 6 June 2012. At that time, IPv6 traffic was about 0.5% of the overall traffic on the global internet. Today, we're sitting at about 43% from a worldwide perspective. That's a pretty big jump in time. And these statistics are from Google, so you can go to Google and look at the IPv6 adoption statistics. If you look at the timeline kind of going up, you see some really interesting like suckouts. Like if you look, you can see there's an opening in between, and in that opening is almost every January. If you look at the January lines and you go up and you see this opening, that is the world shutdown, specifically the US shutdown. So people aren't in their offices, they're at home. And you notice that suckout goes up high, not down low, meaning that the people are connecting to the global internet with IPv6 from home at a much higher rate than they are when they are at work. So we hit some interesting milestones, right? IPv6 is now the dominant protocol in the US, 50%. You see Mexico at 46% and Canada at 39%. Little picture of North America. Source here is Akamai. So this is Akamai's view of the protocols in use from their perspective. And so then this leads us into talking about the mobile and cable providers in the United States. I'm going to kind of focus on the US. And I'm going to show you some interesting statistics. You see T-Mobile at 92%, AT&T, Verizon, pretty high up there as well. Then you look at Comcast, Cox, and Charter, all pretty high, well over 50% in their deployment. Now, this was for a very valid business reason. The mobile providers and the cable providers were busy adding more and more devices to their environment, running out of IPv4 space, and more importantly, they began to design IPv6 as the common protocol or the dominant protocol in their networks to get away from NAT, network address translation. Now, why would a provider want to get away from NAT? There's a number of reasons. NAT requires that state be maintained at the edge of the network, and in some cases, the core of the network. So state is when we are tracking the connectivity of not just the IP address, but the layer above IP as well, the TCP and or possibly UDP. And so in order to track state, I have to reserve memory. And the typical browser in today's modern era will open an IP connection about 30 different addresses and or connections to something like YouTube or Facebook or whatever. There's tons of different connections being opened over IP addresses. When address translation is in use, all of those connections have to be maintained. And so that consumes a ton of memory. It also consumes CPU cycles, holding on to that state. And finally, because of legal reasons, the providers are required to store the translations for law enforcement purposes should a subpoena come up, so that they know who was using which of their public addresses at a given time. So the provider has this huge amount of memory they got to put in the middle of the network, a bunch of CPU cycles burning and churning to maintain those translations. And then they have this burden of storing all those translations. So they looked at that business model and they looked at this thing called carrier grade NAT, which is effectively what I've been talking about. And they decided that it would be more prudent for them from a business perspective to migrate to IPv6 and reduce their costs. So who's driving this 50% dominant protocol now? Literally it was the providers. Now, the providers in and of themselves can't get the job done. So you look to the OS developers. Well, Microsoft, they've been v6 enabled since about 2006. Apple, fully v6 connectivity since about 2009. Google Chrome, of course, v6 capable. All the Linux versions you can think of, and of course the popular handsets or telephony devices, all v6 enabled and preferred by default. So the OS vendors met the providers who were deploying IPv6. So that leads to the traffic that we're seeing, right? But just because you have a network that's at v6 enabled and you have endpoints that are v6 enabled, they need to then go to v6 content. So Google, IPv6 enabled, in fact, maintains some of the global statistics I've shared with you. YouTube, literally the majority of their content is v6 enabled. Netflix, same thing. Yahoo, LinkedIn, v6 only. Akamai, of course, we've seen some of the charts from Akamai. And Facebook, v6 only data center. So the large content and application providers are also v6 enabled. So what you're beginning to see is, okay, we've got this provider market, whether it's mobile or cable. We've got all these operating systems that prefer and enable IPv6. And then we have these content/application providers that are V6 enabled. And it's important to talk about this concept of V6 only, because in that vein, that is the end goal, right? Dual stack is a transition from the legacy protocol v4 to the current standard IPv6. We also see some national strategies for IPv6 helping to push the boundaries. You may be familiar with the US federal government. They put out a mandate 2.5 years ago stating that they were going to migrate to IPv6 only. And folks, let me tell you, it's important that we do that. Why? Because the US invented the internet. Specifically, DARPA, underneath the Department of Defense, within the confines of the US Army, invented what we now know as the Internet Protocol. Two gentlemen that were primarily responsible for the protocol as we know it today, Vint Cerf and Bob Kahn. Now, I know some of you are sitting there going, well, wait, I thought Al Gore did. Gore had a hand in authoring legislation that allowed the internet to open beyond the research and military compound that it was used in. He had nothing to do with the architecture or developing the protocol and the internet as we know it. My point is, the United States gave the world the gift of the global internet. And we need to lead as we're migrating from the legacy protocol to the next generation protocol. Need more incentive? Well, the Chinese have set aside a massive amount of funding to build an IPv6 infrastructure. In fact, they're further along. They're at about 78% based on what little measurements we can get from them, right? So Google doesn't operate in China, so I can't go use the Google statistics or Akamai statistics but there is a site that reports on the Chinese development effort. One thing in our favor is that the state-funded network manufacturer, Huawei, has been pushing an agenda called IPv6 Enhanced. It is not exactly IPv6 that we see from RFC 8200 out of the IETF, but more their own version of IPv6. And so, again, we want to lead and make sure that we're building our expertise, our knowledge, and we're out in front of the cat and mouse game of secure and defend. Portugal has a mandate that they put out in 2016. Germany has been trying to lead the European nations from an IPv6 deployment perspective. Brazil, down in the South American hemisphere, and Belgium. The interesting one with Belgium, if you recall, I was talking about how NAT requires an organization to have to store the translations that have occurred from their clients to their public address space. With Belgium, the drive to IPv6 came from the National Law Enforcement Agency. The Belgian police, the state, the country police, national police, they would issue a subpoena to a service provider for an IP address. That service provider, building the typical NAT environment, oversubscribing the heck out of a single IP address, sometimes to the point of like 16,000 users to a single address, would then send that information to the national police. And they would have to wade through 4,000 to 18,000 entries to try and determine who was using that address at that particular time for the crime that was committed. They said, no more. We can't do this. They mandated that the service provider translate no more than 16 addresses to a public address, or 16 clients to a single public address, so that when they issued a subpoena, they didn't have to wade through a ton of information. Well, that's it. I mean, the providers at that point were like, well, there's no way we can build carrier grade NAT in a 16-to-1 relationship without literally buying an entire data center worth of equipment just to perform address translation. And so they immediately began to deploy IPv6 to mitigate that challenge. And they currently lead the European nations in per capita IPv6 deployment.
Tim, can I ask a question?
Yeah.
I assume certainly law enforcement in the U.S. is faced with that same issue with, carrier grade NAT. Are they making those, or are they making those sorts of pushes to say, hey, you need to move to IPv6 because this is affecting law enforcement?
Actually, I've never seen that outside of Belgium. They're the only nation that I've actually seen that.
Gotcha. Thanks.
Yep. But it clearly doesn't matter because the US providers are already way down that path, right? With the predominant protocol being v6. They kind of took it on themselves.
Gotcha.
So let's look at some of the key differences. And these are the ones I would expect that everybody's familiar with, right? V4 is a 32-bit structure, V6 128. V4, we use a dotted decimal format. In V6, we use a colon hex format. And many of you will look at that colon hex and say, well, wow, how am I ever going to memorize that the way I do the dotted decimal? You will be surprised as you get into V6, as you start to deploy it, how easy it is to actually memorize it. And I'm going to show you in a couple slides how we'll look at the first 64 bits of that 128-bit address and recognize a significant commonality there that'll allow us to remember things a lot in the same manner that we did with the dotted decimal format. So don't be intimidated by these big hex numbers, because once you get to deploying it, it's a heck of a lot easier than you might think just looking at it. Now, some of the key differences that you're going to have to pay attention to. ARP is a broadcast-based protocol, right? It's a companion protocol to IPv4. And if you're familiar with ARP, you typically see an ARP request, ARP reply. So node A does an ARP request, node B does the reply. What happens next? Node B does an ARP request for node A, who does an ARP reply. And so if you've ever looked at a protocol analyzer, right, like Wireshark, you see ARP, 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 ARP all over, right? You got this constant broadcast. And the challenge with broadcast is that all devices on the medium are required to interrupt their process, their CPU, to process that broadcast. So when we were designing IPv6 back in the 90s, we realized that the challenges with broadcast media were significant to how much we interrupt the CPU and impact the performance of the devices. So we moved away from broadcast with IPv6. In fact, there is no broadcast facility in IPv6. You're familiar with the .255 typical broadcast of a /24 in IPv4. There is no .255 equivalent in IPv6. In fact, the neighbor discovery protocol uses multicast technology, so that we're only impacting those that are listening on a specific multicast channel rather than everybody who's on the particular medium. Some of you might be familiar with a PIPA, 169.254. Usually when you see that address space, you're like, uh-oh, the network's not functioning. I don't have connectivity beyond this little local confine. And you can use that APIPA space, 169.254, like in a conference room to do ad hoc networking, right? But you don't have, when you see that address space, you don't have external connectivity. In IPv6, we have this thing called link local. And link local is required by all hosts that operate an IPv6 stack. It's far more useful than a PIPA ever was. Link local is required by all devices, and we'll use that link local address to source our neighbor discovery, our router discovery. Effectively, link local becomes the control plane address for the devices that are participating in IPv6. Now, when you look at that link local address space, FE80:/64, you look at it and I mean, immediately that looks like a layer 2 MAC address. It's not. That's a layer 3 IP address. And it's the most peculiar of layer 3 IP addresses in that it is only significant on the local link. No router can route FE80 beyond the interface. So that's a layer 3 address that's bound to the layer 2 domain for which it exists. And we use that address space, again, for control plane functions within that layer 2 domain. So that's an implication. In order to be globally significant, an IPv6 host must have at least 2 IPv6 addresses. Link local as required for control plane function on the layer 2 domain, and then a global address that enables the device to communicate beyond the layer 2 domain. Next, we look at this RFC 1918 space that everybody should be pretty familiar with, and we contrast that to EULA. There's a big caveat here. EULA is not, and that, by the way, EULA stands for Unique Local Addressing, sorry, and it is not a one-to-one replacement for RFC 1918 space. In fact, in a dual stack network, it is pretty useless because of the way the RFC for address develop or address on host OSs was written. The EULA address space is a lower priority than IPv4. And in order to get EULA to be preferred over IPv4, again, I'm talking dual stack, you have to manipulate the host tables. And anytime you're manipulating host tables, this is not a good thing to do because you can go from one network where you've got manipulated tables to another network that's built properly and things are going to break. And nobody's going to know why they're broken. So we, Hexabuild, have been petitioning the IETF to an errata for RFC 6724, which is the address RFC, to update this. It's going to take a few years before software vendors get that there. Bottom line is that EULA is not a replacement for RFC 1918 and in fact can cause a lot of problems for most networks. And then we have this concept of NAT and NAT port translation that you get from typical IPv4, right? Going from RFC 1918 private to whatever public space. And you may ask, well, where's the NAT for v6? And it does exist. There's two flavors that I called out specifically. NPT v6, which is NAT prefix translation. And it takes the prefix on the internal side and translates it to a public prefix on the external side. It does not manipulate the interface ID, so that stays common from internal to external. It has a use case for small organizations, people who don't have an ARIN membership, let's say, or you have a single provider giving you V6 services in a location. It may make sense to use prefix translation in those environments. You can get NAT66, which is exactly what you'd expect. I've got private V6 on my internal, and I've got some public space that I'm going to translate to on my external. There is no RFC standard for NAT66. But vendors like Cisco and Palo Alto and Fortinet do offer a NAT66 within their firewall products. It is generally not recommended. No sense in going towards something that is not standards-based. And there is no such thing as security through obscurity. And I always get people shocked when I say this. Right? Like, oh, well, I can hide my infrastructure with NAT. Nobody knows. Really? 75% of the bots that exist out there in the world today live behind a NAT firewall. So if you're going to deploy security, RFC 4864 is the right mechanism to look at. And that's called local network protections, right? NAT just got bolted onto the firewall because it was at the edge of the network. It isn't a security tool. It's just simply an address preservation technique that got bolted at the edge of the network where the firewall happened to be sitting. When we move down to the routing protocols, you will see some updates on the routing protocols, specifically in OSPF, right? Version 2 versus version 3 for IPv6. Version 3 can also carry IPv4. Version 2 cannot carry IPv6. ISIS, a lot of organizations are migrating toward ISIS. One of the cool things about ISIS is that you can form an adjacency in the absence of a layer 3 address. So it has become useful for certain technologies, specifically data center technologies underneath VXLAN, et cetera. EIGRP has always had the multi-protocol flavor to it. So generally, we recommend the named version of EIGRP if that's your protocol of choice for IPv6. And then, of course, RIP. Friends don't let friends rip. However, all of these routing protocols have their merit and their place. And in a star topology, particularly in the cable networks, RIP-NG is a pretty good solution. So there are folks who actually use this next generation RIP. I cannot tell you, Pat, it's probably been over 20 years since I've seen a V4 network with RIP running. I'm guessing probably close to the same for you as well.
Yep.
Okay, so let's look at the context of an IP address. It is the core function that enables a system to communicate with another. It's on by default. Routers and firewalls use the IP addresses of other systems to take specific actions. It's not on by default, and configuration is required. And then finally, applications may need to process IP addresses. It may need to read or write from files, put things into databases to be analyzed, etc., and modification may be necessary. So this is kind of a useful chart as you begin your IPv6 journey, in that, first off, all modern OSs ship with IPv6 enabled and preferred by default. Your routers and firewalls need configuration in order to process an IPv6 address. And finally, your databases and or certain applications may need modification to accept that 128-bit address versus the 32-bit quantity that you're familiar with from v4. This means that IPv6 is running in your networks.
Yep.
You've probably seen it if you put an analyzer on a segment and you see all this IPv6 stuff and you're like, what the heck is this stuff doing here? Why is it here? There are ways to disable it, and it just blows my mind how many people put out a tech guide to disable IPv6. It is the dominant protocol. We are now past the point where we want to disable it. We need to focus on enabling it. Also, the only way to truly secure IPv6 is to configure and monitor. If all of your OSs have it enabled and preferred by default, then there is a potential latent threat there. How is it that you're going to contain that latent threat? The best way is to enable and monitor.
Yeah. Tim, can I ask a question?
Absolutely.
My understanding is that the vendors such as Microsoft, their recommendations do not turn it off. Am I mistaken on that?
You are not mistaken. In fact, there are numerous TechNet support articles that say that you may have to enable IPv6 because it is the preferred protocol, particularly on the server side.
Very good.
Okay, so let's take a look at the v4 unicast address. It's a 32-bit quantity. You guys are all familiar with there's some network portion and host portion relative to an IPv4 address. In order to create subnets, I stole bits from the host portion to build those subnets. In IPv6, we have completely altered that thinking. It's 128 bits in length. We're going to go right down the middle at 64 bits. Everything to the right is the interface ID. The interface ID is the new term for what we used to call the host portion. Back in the original days of IPv4, it was called the host portion because there was only ever one network interface card in the original host, right? It was typically Ethernet, could have been token ring, but multiple cards in a network cards in a device was only a far-flung thought that didn't become reality until the late 90s. So with IPv6, we just adjusted it. We don't call it the host portion anymore. We call it the interface ID because the host may have multiple interfaces. So 64 bits is the interface ID. That's the right shifted 64 bits. And on the left side, we have 64 bits that define the network portion. Now you'll notice that I highlight the global routing prefix at 48 bits, and then I give you a 16-bit subnet. This is because 48 bits is the smallest chunk of material that's allowed in the DFZ, the global internet routing tables. So DFZ is the default free zone, the global internet tables. In the v4 space, the smallest portion that's allowed is a /24. If in your internal networks you have some /30, 30s, or maybe some /31s, or even some /25s and /26s, those all get aggregated at least to a 24 before it ever gets to the global internet. And so here in v6, 48 bits of material is enough to uniquely identify a site. And remember, I was saying earlier that you would begin to recognize IPv6 addresses in the same fashion you used to do with v4. So if those 48 bits define a site, you're going to know, boom, the moment you see that 48 bit, whatever it is, right? 2001, DB8, 11, you're going to see those 48 bits and say, okay, that's my site. The next 16 bits is where we play our subnet games. This is still part of the 64 bits that define the network topology. 16 bits give us 65,536 combinations. So I have a 48-bit global routing prefix that defines my site. Site. It doesn't matter how many users you have at that site. That's the site level, right? You could have 4 users in a library. That site gets a /48. You could have a couple thousand users at a, typical office environment. That site gets a /48. And then you have 65,000 subnets that you could create underneath that site prefix of /48. It's mind-boggling. People look at it and think, oh my gosh, that's such a huge waste. Are we going to run into the same problem we did with IPv4? No, we are not. In fact, we're going to reinvent the network layer within the next 30 years. Think about DNS. What does DNS do? It takes a name and gives us an address. Wouldn't it make sense to use a naming structure at the network layer? 30 to 40 years from now, we probably will be doing something like that. In fact, name data networking is a proposal within the IETF. It will take at least 30 years for that to roll out, if it ever materializes in the fashion that's currently envisioned. Now, you may be saying, okay, wait a minute, 48 bits is a site, and I can have 65,000 subnets, and each subnet has a /64 interface on it. That seems wasteful. But guess what? We're actually left shifting in most of the customer environments we're working with. Most of the sites that we're consulting and helping deploy are sitting at a 44 or even a 40 to align traffic types with specific route filtering mechanisms, going back to RFC 4864, local network protections. There's many a valid reason for doing this. And again, you might think, oh, well, that's waste. No, not even close. And I'm going to prove it here in the next slide.
I'm glad you have this slide coming up.
Yeah, this is
because I've been asked that question multiple times.
Yeah, so, all right, now over here on the interface ID, I've given 64 bits. Okay, well, let's take a look at what that means. I'm telling you that the standard LAN size has shifted from a /24, 255 hosts, to a /64. How many host addresses are available in a /64? Well, 18 quintillion. 18 quintillion addresses available for each and every LAN that exists. So I got 48 bits of material to uniquely identify my site. I have 65,000 VLANs. Each VLAN has 18.4 quintillion possibilities. And we're never going to run out. Let's look at some math to prove the point. We're going to attempt to exhaust that space of 18.4 quintillion. And since it's a big number, we're going to go DHCP style, 10 million addresses per second. That's right. I'm going to allocate 10 million addresses per second, every minute, every hour, every day for an entire calendar year. I went ahead and did the math for you. That comes out to 31,536,000 seconds in a calendar year, and I'm allocating 10 million per year now, or 10 million per second. So 10 million DHCP addresses times 31 million gives us 315 trillion, 360 billion addresses per year at 10 million a second. So our math problem is set up. We have a space that's 18.4 quintillion. I can allocate 315 trillion per calendar year. And if you guessed 58,494 years to exhaust one LAN, you'd be on top of it, mathematically speaking.
Tim, I think we've just heard a collective OMG.
Yeah.
Yeah.
Yeah, this is not a Bill Gates moment. 640K is all we'll ever need. No, it's not.
Yeah.
This is verifiable with math.
Yep. One thing I'm glad you walked through this is because one of the things I do is I teach a 2-day network basics class, and it is IP version 4 focused, but I do talk about IP version 6. And one of the things I really stress is that in IP version 4, our customers are having to do a lot of work making their private address space fit within their organization. They'll have to do things like variable length subnet masking, and what I call, they have to do these stupid subnet tricks simply because of that small address space. And I try to tell them that if you go to IPv6, your life is greatly simplified /64 across the board.
Yep.
Yeah. So that in itself is a great benefit.
Yeah, and it doesn't matter if we're talking about a point-to-point link, right?
Mm-hmm.
This is say between two routers. You've got an Ethernet between two routers. It's a point-to-point link /64. Now, some of your minds are being blown right now. You're saying, well, wait, you're going to waste the rest of that LAN space to only use two addresses? Well, look, if it's 10 million addresses per second and it takes 58,000 years to exhaust that space, and we then take that 18.4 quintillion and we say it's an Olympic pool, right? It's a Olympic-sized pool full of water. And I take an eyedropper and I'm going to squeeze one drop in there. In that one drop is 2, 20, 200, 2,000, 20,000 hosts. It's insignificant. It's irrelevant, right? I mean, it's already so enormous that it doesn't matter whether you use 2 or 200 or 2,000. It's just so infinitesimally small compared to the size of the pool. And people struggle to wrap their brains around this. Remember that we have 64 bits on the left side, the network topology. Now, it's a little bit of a misnomer. We do have 64 bits to define the network topology, but some of those addresses have been reserved for specific purposes. So it's not a full, equivalency as it is on the interface ID. But to give you perspective, we are sitting at about 0.2% of the network topology that has been assigned out of the V6 space. So all of the V6 space that's available from IANA to the regional registries and all of the V6 that we've deployed to date, it's only about 0.2% of the total that's available to us. And that's what's allocated, not necessarily what's configured and running. So a crazy amount of address space is still available. It is mind-boggling. You have to then, to really begin to understand these kinds of numbers, you kind of have to look at math problems like this. So let's talk about that interface ID assignment, because this kind of gets people tripped up, right? Similar to IPv4, you can do manual configuration. Oh, wouldn't that be fun? No, especially with automation. Like even in the data center, automation should get us out of manual configuration, but it's available to us. DHCP v6. This is not your daddy's DHCP. It uses different UDP ports. It uses a multicast, whereas the v4 DHCP uses a broadcast. Okay. There is a 4-packet exchange, as you would expect, that enables a host to get a stateful assignment from a server. So that is about the only similarity. There are some other challenges. I'll explain those in a moment. New to IPv6, and you hear about it all the time, stateless address auto configuration, or SLAC. The first flavor of SLAC was this thing called EUI64. And what EUI64 did is it grabbed that 48-bit Ethernet or Wi-Fi MAC address, and it broke it apart. It took the 24 bits that define the vendor and the 24 bits that define the board and separated them. And then it stuffed a 16-bit code in between the two, FFFE. Now, this was cool, okay, especially if you're a troubleshooter. Like the ability to build my interface ID, my layer 3 IP address, off of my layer 2 MAC address. When we think about when we're troubleshooting, those are the two pieces of information we're always looking for, layer 2 and layer 3. And if I can have that right there in that layer 3 address, if I can determine what my layer 2 MAC address is, oh man, that is super cool from a troubleshooting perspective, right? But there's some challenges with privacy. So I'm in Colorado today. What if tomorrow I fly to San Jose, and then Monday next week I fly to DC, and on Wednesday I fly back to Colorado? Let's examine using this method. So here I am in Colorado. I use EUI64 for my interface ID and attach to whatever network topology is given to me by the network. Okay. Then I fly to San Jose tomorrow and I get a new network topology that's in San Jose. But I use this same method to configure my interface ID. Then on Monday, I go to DC, I get a different network topology, but I use this mechanism. And you can begin to see that I'm trackable on the global internet. You can know that that 64-bit interface ID was in Colorado, it was in San Jose, it was in Washington, DC, and now it's back in Colorado. So from a privacy perspective, this stuff is not so good. Enter privacy extensions, SLAC-based privacy extensions. And we've gone through a few iterations of privacy extensions over the years relative to IPv6. Originally, what we would do is we would allow me to configure an interface ID for the topology given to me in Colorado, and I would store that in an MD5 hash. Then I go to San Jose and I would generate an entirely new randomly generated 64-bit ID for San Jose, store that in an MD5 hash. Same thing for DC. When I got back to Colorado, I'd reach into that MD5 hash and I'd grab that originally used randomly generated 64-bit interface ID. And so this was okay, but it pinned me to a location with a specific 64-bit interface ID. And so the more modern version of privacy extensions now has me randomly generating a new interface ID every 24 or 48 hours, regardless of what network I'm on, and I never store what I used. I'm constantly refreshing. So if I sit here in Colorado every 24 hours, I'm going to randomly generate a new interface ID. Now you're enterprise network administrators, and you've got a bunch of hosts that are respinning their v6 interface ID every 24 to 48 hours, depending on your basic configuration, that can be a nightmare for managing who had what address at what time, especially for those of you who have to deal with things like DMCA violations, right? The Digital Millennial Copyright Act, right? If you have to be able to provide proof of ownership of a given address, that can be disastrous. And so we do see a lot of enterprises wanting to use DHCPv6 to avoid some of these challenges with stateless address auto configuration. So let's talk about the differences between the two. So first off, address tracking is a challenge for Slack. As I had mentioned, if I'm changing addresses every 24 to 48 hours, I have to have a way of tracking that. Here's a radius accounting example that could do that for you, right? So you could use radius accounting. You could also do CAM table scrapes or MAC address scrapes. That's my Cisco heritage coming out with the term CAM table, right? You see, you could write Perl scripts that go grab tables and scrape them and bring them back into a database. It seems like a lot of work, right? Could be done, but it's a lot of work. So a lot of enterprises will go to DHCPv6 because you get a stateful reservation, you've got your ability to do your inventory and tracking, etc. But there is one challenge, and that is if you have to support Android. Android does not support the DHCPv6 client still to this day. And I used to have hair, but I've ripped it all out, arguing with one network engineer at Google who refuses to support the DHCPv6 client. You can go back in the annals, back to 2012, when this first kind of broached. And every few years thereafter, this argument continues to come up. And this guy has dug his heels in, and he says he's not going to support it.
So I guess that's not changing for a while until he retires.
Yeah, this guy needs to go away. The Android OS will support something called prefix delegation, and that's getting a little heady into the conversation today. Prefix delegation is a potential solution, and prefix delegation may make its way into the enterprise. What's nice about prefix delegation is that I could build layer 3 access networks. So that's where we may see that happening in the enterprise space. Just to put a point on prefix delegation, think cable provider, okay? Your home cable modem. You might have multiple Ethernet segments behind that cable modem in your home. So when that cable modem boots up, it's going to do a DHCP client request for the WAN side of the cable modem, right? The RF side of it. It's going to say, hey, I need an IPv6 address for this interface. And the DHCP server is going to give it an address to use on the WAN side. The next thing your cable modem is going to say is, hey, I've got 4 Ethernet segments behind me that the customer here might use. So give me a prefix delegation. And so then the DHCP server is going to give a slash, let's say a /56, right? That would enable the cable modem to give out a /64 to 256 different Ethernet interfaces. Of course, there's only 4 in the scenario we're talking about, but generally speaking, when we do prefix delegation, we do it on an even bit boundary. So the most common thing that cable modems are doing is giving a 56 to your home modem. And then your home modem says, okay, I'm going to give the first 64 to Ethernet 1, and the second 64 to Ethernet 2, and the third to Ethernet 3. That's prefix delegation. It's absolutely paramount to the cable providers to the mobile providers. So like from your mobile phone for things like tethering. And this is where this Google engineer has put his stake in the ground. He says that I don't need to support client because prefix delegation is what everybody's going to be doing. And it's true, we may get to that point in the enterprise in the future, but we're not there yet. So there are definitely some challenges if you have to support a large Android environment. And finally, it's important to say that understand the implications of switching methods because there are inconsistencies among the OS as to what is preferred. As you might imagine, Microsoft will prefer whatever information it gets from DHCP over whatever information it sees from Slack. Realize that I can do both, okay? I can give a host an address from DHCP and from Slack. In fact, that's exactly what your cable modem's doing. You're going to get a DHCP v6 address and you're going to get a Slack address from your cable modem connection at home. If you are primarily one method and you then decide you're going to switch to the other method, the caution is that there is inconsistency. Okay, as that transition takes place, some of the OSs might be broken for a period of time. They're not broken forever, right? There's just got to wait for timeouts to occur. So it's just a cautionary tale that if you're doing Slack and all of a sudden you decide, okay, as an organization, we're not going to do Slack in this segment anymore. We're going to disable Slack and we're going to do DHCP v6. Some of the hosts may still be holding on to the Slack information and have not done their DHCP v6 for some period of time. It's not a great period of time, but it is something to pay attention to. Now, in a dual stack environment, we have to be cognizant of how information is conveyed to the dual stack client. Because an application can query DNS either quad A or A over IPv6, then over IPv4, and you can have quad A queries over v6 come back with A and quad A records. In other words, they're not protocol independent. So let me paint a scenario for you, like literally. 10 years ago, you could have IPv6 enabled in your domain. There could be a service in the global internet that is v6 enabled. And so you go out to the DNS for that global service and you get a quad A record and an A record for that service. Well, you're v6 enabled, you got a quad A record, so you send a TCP SYN out to that quad A record that you got. And you're waiting and waiting and waiting because the TCP facility is 7.3. So 7 seconds elapse. I send another TCP SYN. 7 seconds elapse. I send a third TCP SYN. After that 7 seconds, which is now 21 seconds, I decide that I'm not getting anywhere with v6, and so I send the TCP SYN to the v4 address. Boom, the screen paints. Woohoo! Life is good. Is it? I would suggest to you that you have created a PUI, or a pissed off user interface. Could you imagine waiting 21 seconds for a page to paint? It's just inconceivable, right? That's just way too long of a time. So originally, RFC 6555 was dubbed Happy Eyeballs because we want to keep the eyeballs of the user happy. It was updated by RFC 8305, and basically what Happy Eyeballs does is it gives IPv6 a head start. But we're down at the IP layer, not up at the TCP layer. And so we have a 50 millisecond timer, right? If we get a quad A record first, we send that TCP SYN. If we don't get the SYN ACK within 50 milliseconds, then we send the TCP SYN over the v4 address. And finally, if we get an A record first, we're actually going to wait 50 milliseconds. If we don't get a quad A record in that 50 millisecond window, then we'll send the TCP SYN over the A record address that we had received. And so the bottom line here is that Happy Eyeballs keeps us from that very frustrating 21-second delay that TCP was enforcing on us down to this 50 millisecond timer. So part of the talk today was to discuss IPv6 mostly, a step in the right direction. Now, this is a little peculiar because you're going to see that in this IPv6 only network, I'm relying on DHCP v4. So what RFC 8925 does for us is it gives us an IPv6 only preferred option from our DHCP v4 server, specifically option 108. And the client would indicate to the server that it can do option 108. That is, it can do v6 only. I know it's crazy, right? Like I'm telling a v4 DHCP server that I'm capable of doing v6 only. So then the v4 server would check its pool configuration, realize that that particular pool was configured for v6 only, and it will not assign a v4 address. This is a DHCP v4 server. It cannot assign a v6 address. All it's doing is saying that the client knows it can do v6 only, and it's effectively turning off v4 within the client. So I need a router advertisement to tell the client how to do v6. So an RA is a router advertisement. This is different from v4. You see, in v6, the router provisions the segment that it's connected to vis-a-vis the router advertisement. That router advertisement is where you can control and tell the clients on that wire to either do Slack or DHCP or both, depending on the specific needs of your environment. Okay, so the router then sends the advertisement into the layer 2 domain, and the clients then configure their v6 as expected. Now, this is supported in a Windows 11 update, Mac OS 13, iOS. You can see the OSs that support it. Droid supports it. If there is no 108 on the client, then it would use a legacy protocol configuration. So that means that I have to have a few addresses in v4 addresses in that server pool for any client that for whatever reason couldn't support 108, that they could still use the legacy protocol. But because all of the major OS vendors support this functionality now, it's very easy for an organization to begin to deploy v6 only. And if you recall, that's the mandate of the US federal government, is to move to v6 only on the client side of their networks. So this is a step in the right direction because v6 only is the end game, right? Dual stack is simply a transition getting us from v4 to v6, but the end game is v6. And so this is a nice step in the right direction to help facilitate a v6 only environment. I think it's a little peculiar that we had to go to DHCP v4 to, yeah.
You got to do what you got to do, huh?
Right. So Pat, you may not have heard about this yet because it's relatively new. It's only been out about a year.
Yeah, this is actually the first I've heard of the RFC 8925.
Yeah,
But it's good to hear, though. It's good to hear,
it is.
anything that moves the needle.
It does. And because most of the OSs support it, your pools don't have to be a /24 anymore. Right? You could put a /26 or a 28 in those pools just in case there's something that pops up. But you're really not going to have anything pop up because most of the clients on most of the enterprise segments are going to be some form or flavor that I've discussed. Obviously, Windows 10, I'm going to have a bit of a problem. So I may have to do some upgrade there. So this is IPv6 mostly. Now, there's more to the puzzle with IPv6 mostly. And so to introduce the more, I want you to look at what's called 464 XLAT. This is an older RFC, 6877, and you can see 3 blocks here. One on the left is the device. So this is my handset, my phone, my iPhone, my Android, whatever, my phone. In the middle, I have a core network that is IPv6 only. You notice I highlight T-Mobile? 2 reasons. One, that 92% that you saw earlier today about the T-Mobile network, 92% of T-Mobile is V6 enabled. It's because their core is V6 only. And 2, the author of this RFC 6877 is a fellow by the name of Cameron Byrne, who is an engineer at T-Mobile. Okay, so the third block to the right, you see internet services, right? So the global internet, you see some services sitting out there in the global internet. Now I'm going to walk you through what 464 XLAT does for us and why it is tied to IPv6 mostly. So on my device, if I have a native IPv6 connecting to intelligence services that are V6 enabled, Google, Facebook, YouTube, you'll recall I shared with you that those are V6 enabled services. I just ride the V6 only network with my V6 address. Life is good. There are some services that are not V6 enabled on the global internet. And I would use this thing called DNS64/NAT64, and it's exactly what its name implies, network address translation from 6 to 4. What DNS64 does is it intercepts a DNS query to a specific service and doctors it with a bogus V6 address, not really a bogus address, but a internal V6 address that then gets routed to the translation device to perform the translation between 6 to 4. We're all well and good. That's easy. But what about, and many of you may have this, see, that's that NAT64 service there. But what about the situation where you have a legacy application that embeds a literal IP address in its code? And by the way, Spotify, Skype are examples of legacy applications. So the client-side application uses a v4 address that's associated with the specifics, be it Spotify or Skype. In other words, it doesn't do DNS. Now, with DNS64, NAT64, I can intercept the DNS query, doctor it, send it back to the device. Life is good, just basically giving it an address that points to the NAT64 service. When a literal or a legacy application that uses an IPv4 address exists, there is no DNS query, right? If I know the IPv4 address of where I expect the service to be, I don't need to do a DNS query. I just do a TCP SYN. Uh-oh. Right? You see the problem? If I have a v4 address on a v6 only network and I send a TCP SYN, well, it's not going to go anywhere because I don't have a v4 address. And so what you're seeing on the client side is this thing that we call a CLAT, a client address translation. It's a software shim that gives a dummy IPv4 address to the legacy application so that the legacy application thinks it's connected to an IPv4 network. Then the CLAT translates that to a network specific prefix that gets routed to the NAT64 service. This is what makes IPv6 mostly tick in environments where legacy applications may exist. Think federal government. Think how many services they have where they have a literal buried in the client code. And what a challenge that is to have to go clean that code up on the client side to make sure then we have v6 enabled on the server side. This very useful tool allows us to just turn it on the OS and make that translation on the client to that network specific prefix and send it to the NAT64 service at the edge of the network. So together with option 108 and CLAT code, we can begin to deploy IPv6 only networks anywhere.
Very good. Tim, do all modern OSs support CLAT today?
Very good question. Most do. The biggest, most important one, right? When you think about enterprise networks, the number one OS is
Microsoft.
Yeah, absolutely. Hexabuild has been testing and proved for Microsoft the functionality of CLAT working on their wireless and LAN interfaces. So we are proud to tell you, yeah, it's available today and we can deploy it.
Very good. Excellent.
Yeah, we did the engineering testing specifically for Microsoft. In fact, Pat, you mentioned Scott Hogue. You and I were talking about him early. He was the primary engineer doing the lab testing for us at Hexabuild on behalf of Microsoft. So it is functional.
Yeah. Tim, I have a question. As almost all of our customers have a cloud strategy, if it's no more than going to Microsoft 365. But as I look at the big cloud providers, the AWS, Azure, GCP, all of those, they seem to have done a pretty good job of embracing IPv6, although I do see there are some services that are not yet IPv6. Any comments regarding that?
Yeah, they're all getting better every day. AWS is the leader. Azure and Google kind of fight for who's right on their heels. Each and every one gets better every day. You've got a lot of strategies associated with cloud. You'd be amazed at how much address space we throw at cloud on behalf of customers, especially in the bring your own address space. V6, because of its enormity, allows us to do things that we could never do with v4, such as we can assign a unique v6 address to a specific piece of content, to a specific server, to each VM, et cetera, right? So you have granularity to where you can actually, and by the way, Pat, Mark Townsley is a big proponent of this v6 address per chunk of content concept, right?
That's interesting.
Yeah. So you can literally have a big MPEG file, and certain chunks of data are assigned a specific IPv6 address. Yeah, I know, it's crazy when you think about it, right?
Good.
Yeah. So we're given design options that just absolutely could not be possible. Even if so that's very in depth. Like, okay, I'm going to assign an IPv6 address per chunk. All right. So let's go up a level. Let's just say instead of per chunk, I'm going to assign an IPv6 address per service. So I might have a server that's offering 3 or 4 different services, and each service has a different IPv6 address associated with it. You can't do that with v4 either, right? So the flexibility that we're given with v6 from a design perspective, particularly as we're migrating toward cloud, is crazy.
Yep.
There are folks who are talking about single v6 address per transaction. So you're an e-commerce shop, and every transaction you enact burns a v6 address forever. So again, you have 18.5 quintillion per 64. At 10 million a second, it would take 58,000 years. So let's just say you're selling, teddy bears, whatever. And each time somebody connects to buy, you use an IPv6 address and you effectively throw that v6 address away. It was only used for that transaction. Of course, you're storing that information, right? You've got that record of that transaction. But that's it. That address never comes back to play again. Used once and thrown away. I mean, if you were a online retailer and you could sell 10 million of something every second, wouldn't you be happy?
Yeah. That is unique. I had never thought of that, but I can see that.
Yeah.
Yeah.
So, and there's a huge effort for Bitcoin to ride on IPv6 as well.
Very good. There's a question here. So would that lead to not needing ephemeral ports? Interesting question.
So I'm not sure I know how to answer that, because I guess, but it would be ephemeral addresses. I'd have to sit and think about that for a while. I don't want to throw something out there that's murky.
Very good. Okay. Well, Tim, this has been great information. Absolutely. This has been amazing. I'm so thankful that you agreed to come on and talk about this. But why don't you spend just a second talk about what you guys at Hexabill do? Because, I've people consider me the IPv6 nut down here, and I really think we need to move faster at it. And it seemed like you guys have that focused mission on getting people to IPv6, and it sounds like you've got some amazing talent, such as yourself, that can help customers get there.
And I'm probably the least of the engineers. Our team is amazing in terms of the v6 knowledge that they possess. I stand in awe of my peers. We have developed a lifecycle methodology based on the collective experience of all of us having spent at least a decade designing, engineering, and deploying IPv6. And you see here with our methodology, we start off with a transition or / adoption plan. We move into an assessment phase. We have training and education. And by the way, training and education is going to go on throughout an engagement. We develop an architecture and a design, address plan, et cetera, as you'd expect. We take that architecture and design and we move into a proof of concept or testing lab. And from there, we produce a low-level design. So that architecture design, kind of a high-level design, we vet that high-level design in the proof of concept lab and produce the low-level design, which is effectively the cookbook for the organization based on their high-level designs. You'll notice that you move into deployment and operations, and those are not bolded in, right? If we're doing our job right, we have brought you along on this journey, and the deployment and operations of your organization relative to IPv6 is in your hands. So we've helped build the proper documentation. We've identified your adoption plan, your strategy that includes like a business plan, a project timeline, training plans, et cetera. We go through the assessment of your network infrastructure and applications. We are doing training and education throughout. We've helped you develop this architecture because we've trained you enough to the point where you can have input on building the high level design. We go to the proof of concept lab, write the test documents, prove it out, deliver the low level design, hand it over to you. All that documentation's in hand. You've now been empowered to do the deployment and operations. We don't scale to do deployment and operations. We partner with people who provide those services should a customer desire those level of services, because not everybody wants to go on the journey and then do the deployment. Some people will want to have folks participate in that deployment and operations. Hexabuild stops pretty much at the proof of concept because our talent doesn't scale to being out at remote sites configuring V6 week in, week out.
Gotcha. Yeah.
And what we do is we help Fortune 1000 federal, state governments adopt IPv6. We are currently working in the largest civilian agency in the federal government. They're a large healthcare provider in the civilian side of the VA. So we're working with the VA to deploy IPv6. That organization is 380,000 employees and millions of customers. We've been involved there for 2 years. We probably will be there another 2 years just because it's so large. We're also working with a handful of other significant agencies, some of which I cannot discuss. In the Fortune 100, we are working with the world's largest retailer, the world's largest shipper, the world's largest home improvement, the world's largest coffee maker, to give you an idea of the size of some of the companies that we are working with.
Very good.
And we do give back. The IPv6 Buzz podcast is a great place for folks to go get more information on IPv6. The guys get together and talk about all the different aspects of V6. So just about every angle has been covered in that last 146 episodes.
Yeah. Yeah. And folks, I can attest to that because I've listened to those. They're very good.
Yeah, the guys are solid. I'll leave with one last slide. You can reach me at hexabuild.io. And if you would like to connect via LinkedIn, I'm Tim Martin.
Very good. Tim, I have to tell you, if you are indeed the weak link at Hexabuild, then it must be an amazing organization because you have just been a font of knowledge today. Very thankful for you to come on and talk to us. Folks, we're recording, and if you're on my email list, I'll send you a link. Tim, thanks so very much, and keep the faith and keep us moving toward IPv6. And hopefully we'll link up again, and hopefully it'll get a little warmer up there in Denver for you.
Oh, yeah. Thank you, sir. Thank you all
Okay.
for your time. I appreciate it.
Folks, thank you. Y'all have a good day.